Today we are in the fourth day, and it's second session of the fourth day. That is our eighth session of this FDP. For resource person, I'm telling sir, we have started the session by 27/1/2025 on Monday, and now it's fourth day. For every day we are discussing with the different kind of people, different kind of materials, and people from different versatile field. Yesterday we got a person from Brooker India Private Limited. It tells about the X-rays and etc. instrumentation details. And for the second day we got a Sodanupulai, Brahmos Sodanupulai. And the first day we got a person, our Arubagam sir from Central University. He tells about that high pressure material. And the previous session was by Dr. Pantikumar. You might have known about him. He tells about the e-vehicles and our hydrogen fuel, etc. Now we have fortunate to hear from you about your nanomaterials and everything.
Yes.
So I welcome you for this ATAL FDP program, and we thank you for accepting our invitation and precisely come over here for your presentation, sir. And for participants, it's my great privilege to introduce our resource person, Professor K. Seyadaraman. He's very rigorous researcher, I have to tell. He completed his PhD from Anna University, Chennai during the year 2008. Before that, he completed UG and PG from Bharathidasan University. After that, he joined as assistant professor in Madurai Kamaraj University and served as assistant professor in Madurai Kamaraj University for nearly about 10 years. After that, he joined Central University, Tiruvallur. Now he is working as professor and head at the Central University, Tiruvallur Real Science Department. He had more than 2,000 citations, and H-index is about 29, and a very active researcher, and completed many foreign trips. And there are many to research as always. But the thing is that when we involved in some kind of societal activity, that will make a good thing. In such a way that he is a member of MRSI, that is Material Research Society in US, then Physical Society, Japan Society, and of course Indian Association of Growth. And nearly about 10 students have completed their under his guidance, and more. I hope more numbers of students are coming. And he got the honors or awards for UGCS Raman US postdoctoral fellowship. Then from the Japanese government, we got next to Japanese government fellowship, and these are the honors. Of course, he completed PhD in Anna University, Chennai, with good number of peoples. I know number of peoples, the colleague who worked with Seyadaraman sir, and I heard many things about Seyadaraman sir and how sincere he is and how diplomatic he is. So, with these words, I welcome you for this session, sir.
Today I'm going to discuss in detail about the growth of one-dimensional nanorods, titanium dioxide and zinc oxide by using a simple chemical method. A completely research work carried out by our research laboratory and one of our PhD students. How the role of interfacial relationship between seed layer and the growing a nanorod. Generally, nanorods used to prepare by simple synthesis, powder synthesis method, but they're preparing a thin film nanostructures, thin film one-dimensional nanorods on glass surface, glass substrate. It's a bit difficult by simple solution technique. How we carried out to grow such a beautiful nanorods of TiO2 and the zinc oxide, how the dopants are playing a very important role for tuning the different types of nanostructures by the chemical deposition method. Basically, Central University of Tamil Nadu is situated in Tiruvallur. Tiruvallur is very famous for in Asia's largest cart, and the temple is Asia's largest Shiva temple. So more than 360 lingas are in that temple, Shiva temple. I'm from the Department of Material Science. It comes under School of Technology. So we are running a MTech Material Science and Technology course. Eligibility generally MSc Physics, Chemistry, BTech, and the PhD in Material Science. So we are having a very good faculties with a different reputation. It is an interdisciplinary department. Uh, Generally, one-dimensional nanorods and then one-dimensional TU2 nanostructure. One-dimensional TU2 nanostructures mean it is in different form like nanotubes and nanomills and wires and nanorods. So it is considered to be a very attractive candidate for different applications, including photocatalytic degradation of pollutants, photocatalytic CO2 reduction into energy fuels, water splitting, solar cells, supercapacitors, even lithium-ion batteries also, or TO2 manufacture. So dimensionality associated with the zero dimension TO2 nanostructures that gives unique physical properties, and also very importantly high aspect ratio on the structure, chemical stability, excellent electronic and ionic charge transfer, and the specific interface. Uh, uh, as well as the one-dimensional zinc oxide nanostructure, then definitely zinc oxide also has in the form of nanowires, nanorods, nanobells, different one-dimensional structures. Most promising candidate due to their important physical properties and applications prospects. Basically, large surface to volume ratio and direct carrier conduction path of only nanostructures are the key factors for getting into over and other types of nanostructures. Zinc oxide is a direct wide bandgap material having a bandgap of 3.37 electron volt and also high cytonic binding energy at room temperature. Then zinc oxide has a different application field of transistor, ultraviolet photodetectors, and UV light emitting diodes, and the solar cells, etc. Earlier, dye sensitized solar cell structure is just a glass substrate. So people used to prepare a DO2 porous structure, and then on the glass surface, ATO surface. Instead of using a porous structure, then uh, people are trying to get one-dimensional nanostructure on the surface of ATO anode. So that they are trying to get the maximum power conversion efficiency in dye sensitized solar cells. And then just I put the DSSC working mechanism. So another is a quantum dot sensitized to solar cells. So nanorods, one-dimensional nanorods are playing a very important role in quantum dot sensitized to solar cells. So we are sensitizing different material in the form of zero dimension on this one-dimensional surface, so that we will get a beautiful power conversion efficiency in the case of a quantum dot sensitized to solar cells. So advantages of one-dimensional nanostructure, so well-defined crystalline structure, unique optical and electrical properties, and quantum confinement effect. Only structural morphology, and provides a charge carrier move freely along an axial direction. So electronic transport in photoelectrode comprised of single crystal, so even 100 times faster than compared with the nanocrystalline film. So these are all excellent properties which provide aid in electron transport during a device performance using one-dimensional nanostructures. So applications of one-dimensional nanostructures in various devices. It is highly used in photoelectrochemical cells, photovoltaic cells, and photocatalytic activities, light emitting diodes, and then efficient then, confinement of the light by using one-dimensional nanostructures and sensors, especially hydrogen sensors, people using one-dimensional nanostructure, then supercapacitor, and etc. I told you that preparing one-dimensional nanostructure on the substrate is a big difficult task using a very simple solution technique. So no way directly forming one-dimensional nanorods on the surface of the glass substrate. So people are using different types of CDA concept and different uh, temperature, growth temperature for the growth of one-dimensional nanorods. Zinc oxide, not only zinc oxide, also different types of nanorods are for different applications. Then nanostructures, of course, everyone is know that how we are classifying into 3D, 2D, one dimension. zero-dimensional structures. So in particular, 1D structures have attracted special attention due to the confinement of the other two dimensions perpendicular to the longitudinal directions. The important reason for researchers focused on this specific morphological structure for the developing of different devices, already I pointed out, like optoelectronic, photovoltaic, and then light emitting, and solar cells, even in energy conversion devices. So, why we have chosen a TiO2 and the zinc oxide semiconductor materials for the nanorod growth. Already TiO2 is having three different phases like anodized, rutile, brutide, and then among various oxide semiconductor, then it is highly used as a photocatalyst, and then titanite is a very important photocatalyst for strong oxidation power and non-toxicity and long-term photostability. And properties, zinc oxide is everybody knows that it is a large bank of semiconductor material, so widely used in various applications like thin film transistors, light emitting diodes, gas sensors, and the transparent conducting electrode, etc. Importantly, it is possible to grow one-dimensional TiO2 and zinc oxide nanostructure thin film by controlling the synthesis conditions. How we are and then prepared the one-dimensional nanostructures by different simple solutions techniques. I listed out some of the methods and techniques adapted for our growth. Air blast chemical spray pyrolysis used for the seed layer preparation, and electro spray pyrolysis used for the seed layer preparation, and spin coating also used for the seed layer preparation. Chemical bath deposition and hydrothermal techniques, and then generally used for the growth of nanorods, one-dimensional nanorods. So these are the schematic diagram of the deposition method, chemical spray pyrolysis. These people are using this simple technique to prepare different types of thin layers of any type of metal oxides or sulfur, metal chalcogenates. Any type of thin layer we can prepare by using this simple technique. And electrostatic spray pyrolysis is also used to prepare different metal oxide semiconducting layer by using this technique. And the spin coating technique and chemical bath as well as hydrothermal techniques used for the preparation of one-dimensional nanorods of TiO2 and the zinc oxide. And impedance of the work then, in spite of a different one-dimensional structure, metal oxide thin film fabricated using chemical methods. The discussion of interfacial relationship between the seed layer and the growing one-dimensional nanostructure is remains elusive. That even though being a different minuscule, we are having a different papers, that even still the interfacial relationship between the seed layer and growing one-dimensional nanostructure is very less. So interfacial energy, how that hydroxyl and oxide and dangling bond from the seed layer importantly play with the growing particles, and how it is used to grow one-dimensional nanostructures of metal oxides. So controlling the nucleation stage and initial growth rate is very important for the growth of one-dimensional nanorods. So rationally realized that this is a driving force for manipulating 1D morphological structure films. Also the reproducibility of a morphological structure by using this type of work is quite easy. So it leads to the commercialization via the low cost chemical methods. Theme of that work is even though we are having more than 45,000 publications and then available in the material TiO2 and zinc oxide. So exact nucleation mechanism between the seed layer and growing nanorods is still a matter of intensive research. So that's why that we have used this concept for the preparation of one-dimensional nanorods using the seed layer concepts. So the first work, TiO2 based TiO2 nanorod preparation. So we have used the maximum and minimum thickness of TiO2 nuclear layer for the growth of one-dimensional TiO2 nanorods. So intentionally, so we have doped the copper and Mn, and then how the changes happen in the zinc oxide nano and micro rod arrays thin films. So doping, how it is and then changing the structure, nanostructure of the zinc oxide. All are done. We have carried out in to, by the all work is carried out by the one of our students. Tuning a maximum and minimum thickness of TiO2 seed layer for going with TiO2 nanoras is a very that is the key. So, so on the glass surface, scientific content is with respect to the obtaining morphological structure of a deposited film, the interfacial relationship between the seed layer and growing one-dimensional structure is we have classified it as a lower and then high and barrier and destroy. We will see that one by one how it is low and high and barrier and destroy the entire nanoras. So that our research team ensured that the present research work will, is one of the important development of one-dimensional TiO2 nano, visit of the nano micro rod technology in the near future. So first work is we have carried out a lengthy and number dense single crystalline rutile TiO2 nano is prepared by hydrothermal technique. So this is the experimental procedure what we have used, and then TiO2 seed layer prepared by spin coating as well as chemical spray pyrolysis technique. Nanorods are prepared by hydrothermal technique by using two different temperatures, like 120 degrees Celsius and 180 degrees Celsius. So large size and the number dense rutile TiO2 nanorods we have applied. Large size and lengthy nanorod and the number dense nanorod structure surface on glass surface is we have applied. So how that we carried out this experiment? So we have prepared the TiO2 seed layer by spin coating technique. We optimized the thickness is about 13 nanometer, and then by using a chemical spray pyrolysis technique, then TiO2 seed layer is prepared with a thickness of 150 nanometer. One we have taken as a lower thickness 30 nanometer, another is we have taken as a higher thickness 150 nanometer. So a very simple hydrothermal method by using two different temperatures. So that lower thickness is used for lower thickness TiO2 seed layer. We have used 180 degrees, higher temperature in hydrothermal. So we have obtained a large size TiO2 nanoras. In higher thickness seed layer used for the preparation of TiO2 nanoras at 120 degrees Celsius, and lower temperature compared with 180 degrees Celsius. So 180 degrees Celsius nucleation temperature gives a large size TiO2 nanoras, and 120 degrees Celsius gives the number dense TiO2 nanoras on the surface of the glass substrate. So XRD pattern, after we have taken XRD pattern for seed layer as well as the nanorods from the XRD pattern, and then we confirmed that sense of rutile phase of TiO2. But in the case of TiO2 seed layer XRD, we have confirmed that anodized phase also, so that but in seed layer completely rutile phase of TiO2 nanorods are we have obtained. So that nanorod is corresponding to the crystalline tetragonal rutile phase. So that one extra peaks I told you that observed in the seed layer XRD, that it is belongs to the anodized phase. So the higher solution temperature, and then we have observed 110 crystallographic plane orientation, and then for higher solution temperature 180 degrees Celsius, and the crystallographic orientation of nanorod is 110. That lower thickness seed layer we have used, and then at lower growth rate and then higher thickness in the seed layer, then we have obtained 101 crystallographic orientation of TiO2. So this is the then TEM and HRTEM and this is really pattern of large size and dense rutile TiO2 nanoras, and then crystallinity and the growth rate direction of lengthy and dense nanorods were confirmed by TEM, HRTEM and SAD precision. From that we confirmed that crystallographic orientation also, and also we found that nanorods lattice fringes with interplanar spacing parallel to the side wall is about 0.311 nanometer. So this is in accordance with the 110 crystallographic planes of the tetragonal rutile phase. Another is for 001 phases of interplanar spacing is about 0.0 0.290 nanometer. It's quite apparent from the HRT, and it's quite apparent from the HRT images. So this is the lengthy TiO2 nanorods and as well as the number dense nanorods. From the same image, the length of the nanorods we have calculated, it is about 1.5 micrometer, and then and the diameter is about 600 nanometer. But density of the nanorod calculated for the both cases, and then density is about 3 into 10 to the power 4 per centimeter square. And average diameter and the length and the density of the nanorods are calculated for the height. I mean, another case, and then so where we found that nanorod length is 150 nanometer and the diameter is same, but nanorod length is 150 nanometer, but the density is very high here. But the first case, nanorod length is 1.5 micrometer, diameter is almost the same, and the density is very less compared with the number density, nanorods prepared of the glass substrate. Here the density is about 2.4 to 10 to the power 5 per centimeter square. So in first cases, as I told you that in first case, 180 degrees Celsius, the large size TiO2 nanorods, almost 1.5 micrometers size of TiO2 nanorods we have prepared on the surface of the seed layer. And the second case, 120 degrees Celsius growth temperature, then we obtained a number density TiO2 nanorods. So we have taken the stoichiometry of a TiO2 on at 3 points, the bottom and middle and the top of the axial direction of the nanorods, and then we almost if we found the stoichiometry of a TiO2 in the different places, bottom of the nanorods and middle of the nanorods as well as the top of the nanorods. We found all are in a very good stoichiometry, so that we confirmed that the presence of a TiO2 phase purity of TiO2 nanorods on the surface of the glass substrate. So AFM for surface roughness, and also from the AFM we have calculated the height of the nanorod is about 1.5 micrometer and the 600 nanometer diameter we have obtained. So from the AFM images, all the nanorods are well corroborating with the same images. And also we found that using this absorption spectra and band gap value by using UV visible studies, and then we have found that redshift in absorption of TiO2 nanorods as compared to seed layer. Then AB is seed layer, A1, B1 is nanorods. So we found the redshift in absorption of the TiO2 nanorods as compared to seed layer coated glass substrate, owing to the increasing thickness and the length of the nanorods. So the marginal change in absorption value of TiO2 nanorods, it may be attributed to different in number of nanorods on the seed layer coated glass substrate. So from that UV visible absorption spectra, then we have calculated the band value of band gap value of seed layers as well as the rotated nanorods for TiO2. So it is about that. Calculated band gap value is 3.1 and 3.17 for nanorods and 2.9 and 3.01 electron volt for the seed layers. From the work, we found that we have grown these nanorods in two different temperatures, and then 120 degrees Celsius and 180 degrees Celsius. So that from the observations, we found that crystallographic plane growth of rotating TiO2 nanorods by lower thickness of seed layer, subject to the nanorod growth at high thickness. Lower thickness seed layer, then used for the higher temperature, nucleation growth temperature is the 110 crystallographic orientation. The high thickness seed layer with the 120 degrees Celsius growth temperature is the 101 crystallographic orientations. So for different applications, like some of the applications, like in the case of quantum dot sensitized to solar cells, we need a lengthy nanorod. So in some cases, we need a number dense nanorod. From this finding, that we found that varying of seed layer thickness and varying of growth temperature, then it gives a very good change of length of a TiO2 nanorods as well as the density of the nanorods. So Thickness as well as the growth temperature, both are seed layer thickness as well as the growth temperature, both are playing a very important role for the growth of the TiO2 nanorods in different perspectives. And these are some contributions I put here. Then another work is we have carried out initially by using the zinc oxide, I mean spray pyrolysis technique, chemical bath deposition, and the hydrothermal technique we have used for the growth of nano micro rod arrays. And then from this technique, the seed layer of zinc oxide prepared by chemical spray pyrolysis technique and with chemical approach like chemical bath deposition and hydrothermal technique. With the growth temperature is 85 degrees Celsius, and then we obtained a beautiful zinc oxide nano micro rod arrays assembly. In one film preparations and then getting a nano structure as well as micro rods is a very difficult task that we have carried out with controlling the nucleation parameter. So from that from this work that we found that we see the beautifully distributed zinc oxide nanorods, and then on the surface of nanorods we found some of the micro rod assembly also. This is a you see the black portion is completely nanorod assembly, and then on the top of the nanorod, perpendicular nanorods, we found that zinc oxide micro rod also, and then sliding on the surface of the nanorods. So this is also the with a uniformly distributed micro rods on the surface of the zinc oxide zinc oxide nanorods. Here also we have used a seed layer concept. All samples are prepared on the surface of glass substrate, so that from the seed layer XRD we confirm everything that from the seed layer is 002 orientation is a dominant one, but we found that by chemical bath deposition of growth of zinc oxide nanorods, we found a 002 crystallographic orientation. So, and also in the hydrothermal technique also, when we found the 002 crystallographic orientation of zinc oxide nanorods are dominant. So, we just compare whether we have the crystallographic orientation is crystallographic pattern and then nanorod thickness, everything we confirm by 10 and SAD patterns of zinc oxide nano micro rod assembly influence. From the UV visible absorption that seed layer and chemical bath deposition as well as the hydrothermal technique prepared samples exhibit a strong photon absorption near UV region, which attributed to the exciton transition of zinc oxide. Compared with the nuclear layer, that redshift absorption observed in also in zinc oxide nano micro rod morphological structure. So this may be due to increasing thickness as well as the length of the nano micro rod arrays. This is a spectrum, micro Raman spectrum, which is from the micro Raman spectrum, we confirmed the two dominant Raman peaks corresponding to the first order lower as well as the high frequency E2 modes. So a smaller redshift also observed here. It may be due to the longitudinal optical phonon mode frequency of the zinc oxide with respect to the light material. Some conclusions, and here then nucleation energy barrier, we have tailoring the morphology structure evaluation from zinc oxide nano micro rod arrays by using a Mn doping. Here we are using Mn as a dopant. Really, what happened to the solution as well as supersaturation? How that the seed layer is important, playing very important. How metal dopant as well as seed layer is playing a very important role to the growth of zinc oxide nanorod assembly on the glass substrate. So seed layer, zinc oxide seed layer prepared by air blast chemical spray pyrolysis technique, and then here we have used chemical bath deposition. The growth temperature is about 85 degrees Celsius. Undoped as well as Mn-doped zinc oxide, and then micro as well as nanorod assemblies we have obtained here. So this is the same image. So here from the same image, you see that tube, undoped sample. So that zinc oxide nanorods are vertically and beautifully standing here. On the seed layer coated glass substrate, it indicates just the footprint of the seed layer containing high density and homogeneous structure, crystallinity, polar C-plane nuclei. The energetic surface of a specific crystallographic plane or phases can be easily find the phase for sitting or bending under epitaxial relations between the reacting solution, seed and substrate with respect to the lattice mismatch. Here we found that length and diameter of the zinc oxide nanorods are 500 nanometer as well as the 150 nanometer. These are the first one I told you that this is a pure sample and this is a 3% doped element doped sample and a 7% element doped sample and finally 10% element doped sample. What happens when we are increasing the doping concentration? I told you that when we are going for a slight increasing the doping value. In the case of this is a pure one. In the case of increasing the element doping, that almost that we found that more number of micro assemblies are formed on the surface of the vertically standing zinc oxide nanorods. Further increasing of that nanorods and then further increasing of microrods on the surface of the nanorods. Finally, and then nanorods are completely destroyed. Only microrods are with the differentials are obtained. So this is zinc oxide microrods grown on the top of a zinc oxide nanorods, and it's aligned and then parallel to the substrate. This one with the random distributions overall on the nanorods. It is in general, it is well known that large-scale synthesis of nano micro structures is very important for fabricating nano microelectronic devices. The diameter and the length of the nanorods are about 2 micrometer, and as well as the 6 micrometer in the case of 7% doping. This is a 7% doping of Mn. So when the doping percentage is 3, the diameter of the nanorod is decreased and number of microrods are increased with the changes in the aspect ratio and size. But the Mn doping is increased to 7, and then we found that the nanorod is shrinking twice. The diameter of the nanorod is shrinking twice, and almost about 50 to 50 nanometer as compared to undoped one. Undoped one is higher, and then doped one is something lower, and increasing the doping percentage. So that it is the final increasing of Mn doping concentration to 10%. That zinc oxide nanorods are not growing on this seeded substrate. So completely it is microrod assembly only on the surface of the glass substrate. So with the distributed microrods assembly with the different structures like a sheath as well as periodic morphology, and then overall the seeded substrate. From this result, we realized that interfacial energy presumably played an important role during the initial growth of films. So that in general, we compared the degree of supersaturations with the 3 different types. Degree of supersaturation is low, intermediate, as well as the high. The degree of supersaturation is low means that it stimulates the heterogeneous nucleation on the seed layer of polycrystalline zinc oxide crystallites, so that heterogeneous nucleation is possible on the seed layer. So due to that heterogeneous uniform nucleation, so and also lower growth rate, so further we have obtained a beautiful that vertically standing zinc oxide nanorods. Further, it reduces to form and edged hexagonal faces as well as thermodynamically stable somatic zinc oxide nanorods, and these nanorods are elongated parallel to the C axis when the degree of supersaturation is very low. Intermediately, that horizontally aligned monodisposed zinc oxide microrod crystals are promoted on vertical standing nanorods after 1 hour of growth time. So we found that the color of the solution is changed, and the soluble product between Mn, doping Mn, and the zinc is different things that stimulates the different degrees of supersaturations in the precursor solutions with respect to the growth time. So on the percentage of impurity ion, doping play an important role. So intermediate means then slight, I mean, on the surface of the nanorods, and then zinc oxide microrod also started to grow. And then high means at 10% of Mn doping, the the supersaturation is intermediate as well as high. But what happened? Intermediate means that the micro rod is randomly distributed on the seeder substrate. So intermediate means then sometimes seed layer trying to grow into a nanorod, but due to that of high superficial saturation with respect to that of Mn doping, that automatically it demolishes the nanorod growth, and the microrod is randomly distributed on the surface of the seed substrate. So in some places, microrods are trying to build a different microstructure, including a stelliform and sheath-like and flower-like structure. So this is a different orientation of a homogeneous precipitate moving to the high degree of supersaturation. Fast crystal growth at high supersaturation degree induces the formation of a sporadic structure, mostly over microrods by interfacial energy tensions. We found that homogeneous and heterogeneous vibrations are seeded a covered substrate under changing level of degree of supersaturation by doping process in CBT. So when we are increasing further, that automatically that completely we used to get the different types of micro rod assembly. So for the nano micro rod assembly in one substrate, then we used to get nano rod as well as on the surface of nano rod micro rod assembly by simply doping Mn, and we found that degree of changing of degree of supersaturation play an important role for the growth of the nano micro rod assemblies. Then we found that from the AFM images with the different, in order to understand the growth mechanism, so that we have taken AFM and then systematically prepared a series of samples with respect to different growth time, 1.5 hours, 2 hours, 3 hours, so that from the AFM image that 2D as well as 3D AFM image zinc oxide mineral grown on the seeded gas substrate at a growth time of 1 hour. So when we increasing the growth time, that again the problem of micro rod assembly. And so micro rod assembly is very difficult to take a image by using AFM, so that we have used 1 hour growth time of zinc oxide and scheduling for the atomic force microscope analysis. So that from this analysis we found the again length as well as the surface roughness and the length and the diameter of the nanorods. Okay. These are some of the 10 HRTM and ACD patterns of undoped zinc oxide as well as doped zinc oxide. This one is for undoped zinc oxide nano micro assembly, and then this one is for 7% doped Mn doped zinc oxide nano micro assembly. From this case, then we found that beautiful standing nanorods on the surface of the 3D zinc oxide substrate, and then orientation also we found it from the ACD pattern, and then here and then 7% doped Mn doped zinc oxide nano micro infused on the surface of the layer of the substrate. And from that, you see that 2 micrometer. And then nanorod, we found the nanorod as well as the micro rod available on the surface of the glass substrate. And also we found the presentation of the zinc oxide. This is a 10%. You see here 10%. No, almost all we found that micro rod only on the HRTM initiate, 10 and HRTM. And also we found the crystallographic orientation of 10% of 20%. And the lattice spacing also we have calculated by HRTM images. So exotic pattern of a doped and undoped images. You see that this one is a zinc oxide undoped one and 3% dope and then 10%. You see the change of orientation, and then almost that 3% and 7% is the dominant is 0, 0, 0, 2 orientation. But after increasing the doping percentage completely, that orientation is demolished, and then we found that 101 bar 0 orientation of a micro rod assembly after the zinc oxide. So from the Bragg reflections, we found that the preferential growth is along here, and E or M axis of the serial substrate. You see that this image, this is not 45-degree angle image of same image. You see that surface on the surface of nanorod assembly, vertically standing nanorod assembly, and then micro rods are, and then sliding micro rods are on the surface of the zinc oxide nanorod assembly. So that from this and also we have then we observed the invisible absorption for a seeded and then I mean for a pure and undoped as well as the doped zinc oxide nanorods assembly. From that assembly, that we found that the blue shift with increasing doping concentration simply indicate the enlargement of the energy bank of zinc oxide nanomicrorod assembly with the ML doping concentration. So, and from the PL spectrum, pure zinc oxide nano exhibits a combined UV and the broad violet, the blue and the green emissions from the PL spectrum. From this work, then we found that low degree of supersaturation up to 1 hour growth time. Low plus the intermediate degree of supersaturation, and the intermediate plus high degree of supersaturation. Low degree of supersaturation, 1 hour growth, and low plus intermediate degree of supersaturation, and then we successfully grown the zinc oxide nanorods as well as zinc oxide nano microrod assembly thin films on the surface of the glass substrate. But when you increasing the doping concentration to doping concentration to 10%, that we found that completely and then decreasing of zinc oxide nanorods, and then we converted that surface into micro assembly. Surface morphology evaluation of zinc oxide nano micro rod assembly arrays films by human incorporations and under the degree of different degree of supersaturation. So you can see. So observation. Low degree of supersaturation condition in reactant solution should permit the growth of vertically standing nanorods on seeded substrate. Mn doping concentration of 10%, the degree of supersaturation is changed into the intermediate and high, which confine the interfacial energy of the stimulate the benzoprobe efficacy morphological structure. These are conclusions. And we have used copper ions induced how it is induced the reorientation in the zinc oxide nano micro array thin films. Again, zinc oxide seed layer prepared by chemical spray paralysis technique. Nanorods are prepared by chemical melt deposition with a growth temperature of about 85 degrees Celsius. So the copper is doped here and zinc oxide. You see here for a few, again we have observed that zinc oxide nanorods as well as the micro rod assembly. And then, but once you introducing a 5% of copper ions, then on the surface of the nanorod assembly, that you see that micro rods are converted into hexagonal prismatic zinc oxide nano micro rod arrays. So when increasing a 5%, 10%, 20%, so we found that changes. So nanorods converted into nanoplates, and the nanorods are converted into nano microballs, and then when we increasing 20% of dopant, so that completely changing of the morphology we have observed for the growth of zinc oxide. So when further increasing of doping concentration, again then completely destroying the morphology or having something different micro slate structure on the surface of the thin layer. So this AFM image for again surface roughness and then uniform distribution of nanorods on the seeded glass substrate. And we found that stoichiometric of the zinc oxide in the different place of nanorods as well as microrods, and then stoichiometry is completely and then retained in all the nanorod surface and places. And then XRD of the spectra of a few, and as well as copper zinc oxide nano microrod arrays specifically. So major peaks is 100, 002, and the 110 we have applied. This is completely hexagonal side zinc oxide. Potential orientation is in all cases 002, physiographic directions. And so that imply just well crystallized in nanorods along the C axis of zinc oxide. zinc oxide. So another preferential oriented crystallographic plane is reveals that the zinc oxide microrods are lying along the A axis, and from that away some of the crystallographic features in our time. And from there you this is a sample, a few samples and 5% and 10% and 20% and then zinc oxide nanomicrorod as thin films. So from the absorption value around 400 nanometer is a characteristic spectrum. This is a simple characteristic spectrum of zinc oxide structure. And then another work is the one-dimensional zinc oxide architecture of a different transition metals. So we have tried with the different transition metals. And do zinc oxide seed layer. Here, zinc oxide seed layer prepared by electro spray pyrolysis technique, and then growth nanoradars are prepared by hydrogen technique. So zinc oxide seed layer is a semi-image of zinc oxide seed layer, and then mesoporous structure on pure zinc oxide seed layer nanorods. So you see here how hexagonal nanorods assembly we have obtained on the pure seed layer. Aluminum doped seed layer. Then what happened? The different doped seed layer we have used here, and then growth, and the different doped seed layer used for the growth of nanorods. Then you see the change in structure of the nanorods of zinc oxide with the different dopings like aluminum as well as cadmium, copper, and indium. So indium, in the case of indium, and completely destroyed the nanorod assembly, then completely converted into the microrod assembly. So beautifully vertically aligned nanorod. So on the surface of the nanorod, it is hexagonal, almost like it is like a tube-like assembly. We have tiny cadmium pieces and copper pieces, something different. Doped seed layer we have used for the growth of the different nanorods. So nuclear nanorods are not in spherical shaped nanoparticles, so that in this case of indium doping, so that so different types of nanorod assembly, not nanorods, so microrod assemblies we have applied in the case of indium. So this is an XRD pattern for zinc oxide architectural functions on the doped seed layer substrate. So all cases we have applied a beautiful diffraction fix. 002 orientation crystallographic plane is the dominant one for the growth of nanorods on the surface of the seed layer, different group zinc oxide seed. So this is just UV absorption on the microramen from the ramen, and then what are the, I mean, just to confirm that the substrates as well, and then frequencies and more. So electrical studies also we have carried out for the different zinc oxide structure, and we found that doped, I mean, this is for doped seeded substrate. So the from the spectrum, how mobility as well as resistivity and the carry concentration of the pure aluminum, cadmium, and the copper and the indium doped and nanorods are changing with respect to that of doping. So that pure is having so carry concentration is very high, but mobility is low. But after that, in the doping and the of different metal ions, then we found that increasing of carry concentration, decreasing and increasing. The same feature is observed for all the doping cases also. Just as finding out the carrier concentration, carrier charge carrier mobility, resistivity, conductivity of all the doped seeded substrates. So overall conclusions, what one-dimensional TiO2 nanostructure thin films, and we have used lower thickness of TiO2 seed layer subjected to TiO2 nano growth at high temperature. High thickness seed layer of TiO2 used for the TiO2 nano growth at lower temperature, but high temperature, then the particle size is small, I mean lower thickness of the seed layer, so growth rate is high. So at high temperature, that is the reason lengthy and large size retail nanorods are grown in the environment. But then the second case, that when we increasing the thickness of the seed layer, particle size also increase. Additionally, at low temperature, growth rate is low. So therefore, at low growth rate, the number of nucleation find out on the higher thickness nuclear layer, which promote the higher number density nanorod growth on the surface of the seed layer. So copper doped zinc oxide nano and micro-rod array extension. Copper ions intentionally introduced for the growth of zinc oxide nano micro-rod array growth. Chemical solution environment for doping. Copper ion disturb the zinc oxide growth rate and they change the interface relation between nuclei as well as growing nanorods and destroy the morphological structure. The same way we found that in the case of human also, when introducing human doping, with respect to reducing diameter of the nanorods, the interfacial energy barrier was observed. Importantly, at 10% of human doping, interfacial relation totally completely stopped due to higher computation between the human and the zinc ions, which only induces the micro-rod assembly of the feeder substrate. Again, metal ions, we tried for the metal ion doped seed layer, and on this metal ion doped seed layer used for the growth of the nanorods, we found the different types of zinc oxide nanostructure and applications, different applications. The complete work is carried out by one of my students during his PhD in Soundarajan. It takes a lot of time and patience, so that we have designed some of that other work also. Due to time, just I start here. So all the structures are prepared on the surface of the gas substrate. So we are not using any sophisticated vacuum technique for the preparation of nanorods. We have used only a simple solution techniques. So on the surface of the glass substrate, it's very difficult to grow nanorod on the surface of the just glass substrate. We have used a seed layer concept, and also then we have successfully prepared nanorods assembly on the surface of the seed layer. And so this is the one of our work. Number of work we have carried out, and that is for different applications. So just I presented here for the growth point of view. So changing the solution, changing the solution concentration, changing the solution temperature, and the key observation of the growth of nanorods inside the solution technique. So one can easily grow any type of material in nanostructure form, like a nanorods, one-dimensional, or different types of nanorods. And then nano micro rod assembly is very difficult, so that is highly useful for the different nano micro rod applications. The growth point only I just presented here. We have carried out some of the applications, so that successfully we have carried out applications of solar cells and also sensitivity. With that, I will just stop here, and if you have any queries, clarifications, I will.
There are many appreciations on the chat box.
Okay.
All appreciation goes to you, sir. Thank you very much.
Thank you, sir.
It was very nice and wonderful presentation. And we are trying to make this as a YouTube video, and we will post it because as per the norms of the AICTE, we have to do that.
Yes.
Right? After that, I will share the link to you also.
Yes, sir.
Thank you for seeing me after a very long time, sir.
Yes, sir. Thank you, sir. Thank you for giving me this wonderful opportunity.